Hello friends, now welcome in my new video lecture of power system stability. It is a lecture number 3. In previous lecture we have covered these three major topics, which is synchronous generator connected to infinite bus. Here we have to discuss about the active power received at receiving end and the reactive power expression at the receiving end, or how much the maximum power which is injected to a power network by a synchronous generator. So if your synchronous generator is connected with an infinite bus or a constant voltage bus, then during the control operation, how much active or reactive power will be injected by that synchronous generator to the infinite bus, or what will be the maximum value of the active power which is injected by a synchronous generator to the grid, we can analyzing on the basis of these three equations. Then we have discussed the power angle curve, where the power angle curve is basically a representation of the relationship between the power and angle. So basically the active power P is equal to EV by X sine delta, where the active power injected to the network or the maximum power generated by any synchronous generator is based on the load angle. So if your load angle is a 90-degree, in that situation you can inject the maximum power to the network by a synchronous generator. Or this relation also give the establish a relationship. This relationship is also applicable for the transmission line power flow. Thereafter, we have discussed the swing equation derivation, how the swing equation can be derived with the help of the two constant, that is moment of inertia and the angular moment, and on the basis of that swing equation we can easily understand the dynamical property of a synchronous generator, especially the dynamic behavior of the rotor during the disturbance, or if your steady state or the transient state stability points are affected, or the operating point of any synchronous generator is affected due because of the disturbances, then how we can understand the dynamics of a synchronous rotor. So these are the topics we have already covered in the previous lecture. Now in this lecture we will discuss these two basic topics related to power stability, multi-machine system and machine swing in the unison. These two topics is basically uh, the you can say that the topic is basically representing the behavior of any power system network with a multiple machine if it is connected with the network. And the second point, machine swing in the unison. As we know, there are number of machines which is connected with a grid. So if all the machines are swinging in in uniformity or with together coherently in a due because of any disturbance, then how we can analyze that situation into the network. So the first topic is multi-machine system. So in multi-machine system, the common system base must be selected. If we are talking about the multi-machine system model, then firstly we have to assume that there are several machines which is connected with the network, and for all the machines the base is common, or the power rating means power base means as the MVA rating of the all the generators. The base value of the MVA rating of the generators is common before going to the detail of the multi-machine system. So let us G is machine rating base and G system is the system base. So there are two bases. One, G machine, that is the base rating of the machine, and G system, this is the base of the entire system. So by the swing equation we have already derived in the previous lecture. So by the swing equation we can rewrite these equation as G machine by G system is H machine upon pi f. This term will be here d2 delta upon dt square is equal to pi minus pe G machine upon G system, means you have multiplied the G machine upon G system on both the side of the swing equation, and it can be written as equation number 21. Now H system upon pi f is equal to d2 delta upon dt square, means this term will be equal to Pi minus Pe per unit on system base. So if we will consider as a system base, so we can represent this entire equation 21 in a form of per unit system, and the per unit equation can be represented by the this equation number 22. So where H system is basically G machine upon G system into H machine. So that this three term will be represented by H system here, and this can be represented in a form of equation number 23. Okay, let us assume there are two machines which is connected with the same system, having the common base for both the machines, and both the machines are swinging, or the rotor of the machines are swinging in a synchronous manner or swinging in the unison, uh, corresponding to a disturbances. So we can say that the swing equation of machine 1 can be represented by equation number 24. Similarly, for the machine number 2, it will be represented by equation number 25. And because machines common base are common and they are swinging in the unison manner, so we can assume that the delta 1 is equal to delta 2 is equal to delta, which is equation number 26. Now add equation 24 and 25, then we will by putting the value of equation number 26, then we will get the equivalent swing equation for the entire system, which is H equivalent upon pi f d2 delta upon dt square equal to Pi minus Pe, which is equation number 26. So the equivalent uh, H constant for the entire system can be represented as G1 machine upon G system into H1 machine plus G2 machine upon G system H2 machine, which is basically equation number 20. So this topic represents concept which is related to swinging behavior of multiple machine which is connected with the same system. Then in that situation, for analyzing the behavior of entire system or the dynamics of the entire system corresponding to any disturbances, we will evaluate the equivalent H of entire system. So this concept is very much useful for analyzing the interconnected network during the disturbance, and that this equation also play an important role in the power system stability analysis. So till now we have discussed the two major points. One, if number of machines are connected in a system, then how we can derive the swing equation or then analyze the dynamics of the machine's rotor behavior with respect to any disturbance. And the second topic, this is machine swinging inhibition, is if any disturbance occur, then how the rotors are swinging into the system, and how we will analyze the rotor dynamics by the help of swing equation and role of the equivalent H constant in power system transient analysis field. So now on the basis of these mathematical discussion, we will try to understand or solve some problems which is related to swing equation and the interconnection with the infinite bus, or it is based on the multiple machine interconnected with it. So let us assume the first problem. A 60 Hz 4 pole turbo generator rated 100 MVA 13.8 kVA has inertia constant of 10 mJ per MVA. So now find the stored energy in the rotor at the synchronous speed if the input to the generator is suddenly raised to 60 meg. Suppose if the generators if the input of generator is suddenly rise in 60 megawatt or electrical load of 50 megawatt, then find out the rotor acceleration. So we require to evaluate the acceleration. Third, if the rotor acceleration calculated in part B is maintained for 12 cycles, then find the change to torque angle and torque speed in RPM at the end of this period. So the entire problem is asking a three major thing, means how much stored energy is there. Now what will be the rotor acceleration, and third, if rotor is accelerated and it is for the 12 cycle, then what will be the torque angle and the rotor speed in rpm for this particular time. So for solving that, suppose stored energy is what, g into h, where g is the generated power is 100 mva and h is given here. So the stored energy is 1000 mj. So first part A will be resolved. The total 1000 megajoule stored energy is there. Now the second part, it is asking for the acceleration power. So PA is what, PI minus PE. So because generator input of generator is suddenly raised to 60 megawatt from the 50 megawatt. So 60 minus 50 is 10 megawatt. So we can say that the power, accelerated power, will be the 10 megawatt. Now we know that M is equal to GH, means the stored energy, divided by 120 F. So 100 into 10 upon 180 into F, 60 Hertz is given. So total this amount of the M constant is there. Now M is equal to M d2 delta upon dt square is equal to PA. We have already evaluated the PA and we have evaluated the value of M. So we, by this expression we can easily get the value of d2 delta upon dt square. So now if we put here d2 delta upon dt square, the total value is 108 electrical degree per second square. Now that is alpha is equal to acceleration is 108 electrical degree per second square. Now the third part, for the 12 cycle, 12 upon 60 is means time will be 0.2 second. So change in delta is what, half alpha delta t square. So half into alpha cube value from here, and t square is this one. So you will get the alpha is equal to 108 electrical second. So total load angle will be 2.16 electrical degree. So we can easily get the value of the delta. Now that alpha is equal to 60 into 1.8 by 360 rpm per second, is it is means that is the 18 rpm per second. So that rotor speed at the end of the 12 cycle is 120 f by p plus alpha t square. So we will get the answer is equal to 1803 into 6 rpm second. Similarly, second problem, a 400 MVA synchronous machine has H1 is equal to 4.6 mj upon MVA and 1200 MVA. Machine has S2 is equal to 3.0 mj upon MVA. The two machine operate in a parallel. The question is for the two machine which is operate in a parallel in a power plant. Then find out the HQ relative to this. The entire solution is total kinetic energy of two machine is what, 4.6 into 400 plus 3 into 1200 is megajoule. Now using the formula given in previous equation number 28, so H EQ is equal to 400 by 10 into 4.6, this one. So H equivalent you can evaluate from here. The equivalent inertia relative to 100 MVA base is H of system base. So we will get the H equivalent is equal to this value. Similarly, problem number 3 is also given, which is based on the formula. You can easily understand the problem which is given here. Similarly, again one problem which is the sending and receiving in voltage related problem, and you have to calculate the steady state power that can be transmitted over the line. So by the means it is asking for the maximum power problem. So again you can directly put the value of uh, put the values from the formula and directly solve it. So now problem number 5. The single line diagram which is shown here, all the values are per unit on a common base. Then power delivered into the bus number 2 at the infinite bus having the voltage of per unit. It is a problem in minus problem is 1 per unit and at zero point 0.8 power factor lagging. Obtain the power angle equation and swing equation of the system. Neglect all the losses. So it is an infinite bus problem. For solving this problem, firstly we will find out the impedance diagram of the entire system, and the entire once you get the impedance diagram of the entire system, then x equivalent of the system is this per unit. Now cos phi is given here and phi is equal to this one. So current into bus number 2 is 1 upon 1 into zero point 0.8 angle this one. So we will get directly the current which is entered to the infinite bus. Now voltage Eg is given by Eg delta, then Vg is equal to 0 plus this one by simple writing the mesh equation for the entire system voltage equation. So by solving this, you will get Eg is equal to 1.463 and delta will be equal to 20 degree. So P is Eg V2 upon x equivalent sine delta. If you put the values here, then you will get the final value of the power which is injected to the infinite bus. P is this much. Now from this equation, swing equation, we will have a equation of it. If the desired work of electrical degree, then equation 1 can be written as this form. Now hence Pi is 1 per unit mechanical power input to the generator. So that is H upon 120 F, this one 1 minus, and the Pe is here, then answer will be this one. Now, as a verification of the result of at steady state, Pi is equal to P is equal to 1, that is 2 this one, the delta is equal to 20 degree. That is already established or already find out. So this is the overall concept related to the swing equation. Some of the numerical problem we have seen here, which is directly based on the by the help of solving the formula for the swing equation, multi-machine problems, and the machine connected with the infinite.